Awesome. Okay, we have participants coming in.
And we are live.
Thanks, Owen, for setting up. Hello, everyone. We're just waiting for a few seconds for all the participants to come in, and then we may start our webinar. So, awesome. So, yeah. Hi, everyone. Thanks for joining our seminar series. We are being recorded and live streamed on YouTube right now till 1 p.m. ET. So if you do not want to be recorded, please feel free to exit Zoom and watch the seminar on YouTube. I'll just pause for a few seconds for anyone to leave Zoom and join YouTube now. Thanks. Great. So, yeah, a quick note on Trustworthy ML Initiative. We are a bunch of researchers, students, postdocs, and professors who are excited about the broad area of trustworthy machine learning, and we care about all the different aspects of research that is associated with trustworthy ML. Our initiative has few goals and efforts. We try to provide a curated list of tutorials, courses, and papers on our website for anyone to have free access. We provide a platform for Rising Star Spotlight talks and Twitter highlight series to highlight papers from aspiring PhD students. We have an active Twitter handle for everyone to have open discussions and debates. And finally, we also hold symposiums and workshops like the one we had a few weeks back to celebrate our first year anniversary. So with that, I'll walk to today's agenda. We have Nicholas Carlini today, and we are very honored to have him as our guest today. We'll be having his talk from 12 to 12:45 ET, and then during that time, feel free to submit, upvote, and comment on questions using the Zoom Q&A tool. From 12:45 to 1 p.m. ET, we'll be having some Q&A sessions and some moderated chat with the speaker. And after 1 p.m., we'll have an optional social, so feel free to stay or leave after the talk ends. With that, without further ado, I would now like to introduce Nicholas Carlini. Nicholas is a research scientist at Google Brain. He studies the security and privacy of machine learning. And for this, he has received best paper awards as ICML, Usenix, Security, and IEEE S&P. He obtained his PhD from the University of California, Berkeley in 2018. And without further ado, I would now request Nicholas to take it away.
Hi, thank you. Thanks for the introduction, and thanks for inviting me to come talk. So I'm excited to come talk today about some work that we've been doing on the privacy of machine learning. So this talk is going to cover 1 to 3 papers, depending on how far we get. I've put the stuff I think is most interesting up front, so I prefer for people to sort of ask questions, and I'll pause a couple points to see if we can take questions. And if we don't get to the stuff at the end, that's fine. I'd rather have a discussion with everyone that's here than just run through slides and not care about all of you. The general thing that we're going to try and do is we're going to try and extract training data from neural networks. So we all know that. Actually, this part of the paper is joint work, I should say, with like 10 people or something like this, 11 other people, and yeah, this is one of the biggest collaborations I've done, and it really sort of needed everyone. We all know that machine learning models are now being trained on things like our medical images, on things like our text messages, our emails. And if we're going to be doing all of this, it raises the question, what happens if there's someone out there in the world who can interact with a trained machine learning model that has been trained on some sensitive information? Is it possible for this person to query the machine learning model in some way so that they can reveal sensitive information about the training data? So there's this XKCD I liked from a couple of years ago that has a person typing at the keyboard, long live the revolution, our next meeting will be at, and you have a hypothetical smart compose-like system that's completing the docs at midnight on June 28th, as if it's memorized this being the answer that someone else had typed. And so the basic question in this talk is like, is this real? Like, is this something that actually happens, or is this just a comic that we like to say, oh, that's fun, something that could actually happen? And the basic result of this talk is to show that we actually could do this. Okay, so let me get started by explaining the first piece of this, of showing how we can do this in the case of language models. So in the case of a language model, what we're going to do is it's a very simple two-step attack. The first thing we're going to do is we're going to generate a lot of data, and then we're going to do something that's called membership inference. So let's get started with the first piece on generating a lot of data. If you're not aware of what a language model is, the purpose of a language model is to be able to generate text. It's trained on large amounts of text data, and the purpose of a language model is to generate lots and lots of output text. Most language models are good, and they generate lots of high quality text. And so all we're going to do is we're going to use the fact that we have a language model to generate a lot of text. And this is very easy because this is what the model is designed to do in the first place. So we just get a huge amount of text, and now we have a bunch of text. Now what do we do with this? What we're going to do with this is we're going to run what's called a membership inference attack. And this is really where all the magic happens. The first piece is trivial. You just generate lots of output. The second piece, we have to decide which of the output that comes out of the model is training data, and which of the outputs that come out of the model are just actual benign things that come out of the model. Okay. So how do we do this membership inference? What it looks like, when it works, is actually quite nice. It just sort of will highlight for you specific examples that say, like, these things look like sequences that were memorized, and it will say everything else looks like it's fairly benign. But what does it actually do? How do we make this magic thing happen? What we do is we rely on the fact that language models not only generate text, but they also will give us probability distributions for all of the words in the sentence. So let's imagine I have some sequence that I'm feeding to the model. It's like, this is a banana, followed by a special end of sentence token. What a language model will give me is it will tell me the likelihood of every single word in this sentence. And as a result of this, I can multiply all of these probabilities together to get a final probability distribution, or a probability score for this entire sentence. And so I end up with something that says, like, this is a fairly likely sentence because all of the individual pieces of this sentence were likely independently. Okay, so this is good. So what are we going to do with this? The idea is that it turns out that training data happens to have higher likelihood than non-training data. So why should we expect this to be the case? Well, because the objective of training a machine learning model is to minimize the loss on the training data sets. And if you're trying to minimize the loss on the training data, then what this means is you're going to make sure that all of the examples in the training data set have fairly high likelihood. And so on average, training examples are going to have high likelihood. Now let's consider something that's not a training example. If something's not a training example, it may have high likelihood by chance, but there is no reason for the model to be encouraged to make this example have very high likelihood in particular. And so on average, if something is not very likely, then it's probably not training data. Now, this is the way most training membership inference attacks work. There's an entire research direction that's focused on generating membership inference attacks, and they do a lot of work in that space. But we have one particular problem with it, which is that if we just measure what's called perplexity for language models, this is this likelihood measure, we're going to come up with weird things like this. Let's imagine I have a model and I ask for the probability of the sentence, this is a banana, and it says the probability of this is like 1e minus 5. So this is, kind of rare, but in the space of all text is probably fairly benign. And let's imagine I also have another sequence of text, but this text looks completely bizarre. that has the same likelihood. As like a human looking at this, if you told me these two facts, I would be very surprised that the second one had likelihood 1e minus 5, given that the first one also had likelihood 1e minus 5. Like I have probably in my life said something like this is a banana many, many times. I have never before in my life said /73/C9/47/BB going on. And so this probably means that if these two things have similar likelihood, it probably the second thing was memorized in the training data set. And so we'd like an attack which can distinguish these two facts. Okay, so this is an intuition. How are we going to actually do this? What we're going to do is we're going to consider the ratio of the likelihood of two different models. I'm going to have two models, F1 and F2. F1 is going to be some model I'm going to try and attack. And F2 is some other model. So maybe some other neural network trained on different data, maybe some text compression engine, just something else, which is reasonably good. And I'm going to compare the likelihood of the text under these two different models. Basically, F2 is this formalization of me as a human being surprised by the second sentence, but not the first. And so what I end up with is, any plausibly good machine learning model will probably assign roughly the same score to the string, this is a banana. And so I'll end up with a likelihood ratio somewhere around 1. On the other hand, the first model, I said, has likelihood ratio somewhere around 1e minus 5. But the second model, which probably was trained on different data sets, and probably didn't see this exact sequence, is probably going to have a likelihood score much, much, much lower. Let's say somewhere around 1e minus 10. And then when I consider the likelihood ratios here, I'll end up with something that's roughly, 10,000. This is much, much, much bigger and much more surprising now. And so what I'm going to try and do is I'm going to say that it's likely that this second sequence is memorized, not because the absolute number of 1e minus 5 is very, very big, but because this likelihood ratio is very big. And this is essentially how the attack is going to work. We're going to do this, this process where first we start with generating lots of data, and then we're going to score all of the text that we've generated with these two different models, compute the likelihood ratio, and go from there to say which of it is memorized and which of it is not. All right, now, it's pretty clear to say that this is not an optimal attack. Like, all we're doing is we're just asking the model to generate normal text, and then seeing if the model happens to just benignly output memorized training data. It's pretty clear that if you were an actual adversary, you could probably do a lot better than this by encouraging the model to somehow spit out more likely memorized stuff than non-memorized stuff. But at the very least, this is going to serve as a nice baseline for the minimum amount of memorization that you should expect the model to see. Okay, let me pause for 1 second and just see if there are any questions on the setup of how we're going to do this before I go to the actual attack measurements.
So maybe I can ask some clarification questions, Nicholas.
Yeah, go ahead,
so
please.
The models that you mentioned, F1 and F2. So I understand they are like two different models trained on the similar training data settings, but they were what were the main difference between the models? Were they initialized differently or optimized differently?
Yeah, great. Yeah. So in the paper, we consider a lot of different things. One thing we consider is just a smaller model. A smaller model maybe intuitively memorizes less things, and so is less likely to memorize particular training, the same things. The other thing we consider is actually like a really, really simple language model of just text compression. So take the zlib text compressor and just try and compress the string to be as small as possible. This is in some sense a language model, because what it's doing is it will, if you give it like a compressed string, it will expand it out to a longer string. But it's a really, really terrible text compressor. But what it will do is it will identify, language models tend to be happy, assign very low likelihood scores to the repeated strings x, 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 because it's sort of very easy to predict this is going to continue going on forever. And we want to filter these out as being non-training data. And so what text compressors will do is it will also say this is a very, benign sequence and is going to filter this out as not being something that's interesting and memorized.
Right.
So you can get different properties from different other models F2. And that's part of what the paper tries to study.
Thanks, Nicholas. So I think we also have a few questions on the Q&A tool. I think Xian is asking a similar question, which I think how to pick up F1 and F2, which I think you elaborated very nicely. We have a second question from Mukit, and it says, are more frequent texts be memorized or less frequent ones? And can you also help with explaining more about memorization?
Okay, yes. So is more frequent text memorized more often than less frequent text? When I'm going to take that question to mean is text that's repeated in the training data more often to be repeated or memorized than text that's repeated less often? And the answer here is yes. And I'll actually come back to this in just a few minutes.
Perfect. Thanks, Nicholas. I think, yeah, those are the questions.
Okay, great. Yeah, so now let's sort of have the attack set up. Let's go to the measurement side of things. So the model I'm going to attack is GPT-2. This is the F1 model in the previous slide. This is the model I'm going to try and extract the training data from. And there are basically three reasons why I want to attack GPT-2. The first of these is that GPT-2, at the time we did this work, we started this paper in 2019, was the best model anyone had ever released. And before this, there has been lots of privacy analysis, but most privacy analysis was privacy analysis of models the researchers had trained themselves. I am a privacy researcher also, and I have no idea how to train language models that are good. And so I've written papers on privacy of language models, but it's entirely possible that when I say that language models are non-private, the only thing that I could actually infer from this is language models trained by privacy researchers are non-private. Like maybe if you sort of know what you're doing and you train a really good model, you can actually make it private because they're trained to have as good generalization as possible. Maybe this solves privacy. So by doing an actual state-of-the-art model, we can rule this out. The other thing that's nice is the model was public. Anyone in the world can download the model, and so it's not like we're doing some sensitive research that was going to cause significant harm because other people couldn't have done the work as well. And the final reason why, again towards this mitigating harm, is that the training data that GPT-2 was trained on came from the public internet. So when OpenAI trained GPT-2, what they did is they scraped the internet for text that they could find online, constructed a 40 gigabyte training data set, and trained the model on this text only of data that was on the public internet. And so what this means is that if we succeed in our attack, if we sort of are able to exceed beyond our wildest dreams, the best thing that we'll be able to do is extract data that was already public on the internet. And so we're not going to cause some significant harm to people by being able to extract training data from this model. But on the other hand, the 40 gigabyte data set that was actually used to train the model was never released by OpenAI. And so what this means is that we will not be able to accidentally cheat in our attack by having access to the 40 gigabyte training data set at attack time. We sort of have this as an actual test set that we don't have access to, and then we worked with some collaborators at OpenAI to actually get access to the model, or to the data set to verify the correctness of our results. But we only did that at the very end. So this allows us to sort of not cause harm, but also still be able to check our answers. Okay. So the paper is actually focused on something that's fairly technical of how you choose these models F1 and F2 and some various combinations of attack results and stuff. I'm not going to talk about this as much because it's not as interesting. I'm just going to give you the high level overview of the interesting set of results. And in particular, I'm missing one set of results. Okay, I'll just talk for 1 second on one slide I forgot to put in. So the main result of what we're able to do, I guess you can kind of see it if you sum up along the columns. What we are able to do is we find 600,000. We sample from the model 600,000 times. And then what we do is among these 600,000 things that we sample from the model, we filter them down to 603 examples of memorized content we are able to get out of the model. So what we find is 603 memorized training sequences from the model. And the limiting here factor is of 603 is that we had to manually review each of them to detect if they were memorized or not. Because you can have things like one character substitutions, or you can have things where the model finds something that's very, very, very close to something that's training data, but not quite. And so the 603 number should not be taken as the amount of memorization in GPT-2, but should be taken as GPT-2 memorizes lots of things, and we have here 603 examples we can look at. And the kinds of things that are memorized, because this model was trained on the internet, are things like news articles, are things like pieces of code, are things like licenses that are repeated a bunch. But also we find things like personally identifiable information of people who have chosen to put their data on the internet, of things like physical addresses, email addresses, social media handles, these kinds of things. And what we were really mainly surprised by was the diversity of content which was memorized, and that we found just really, really wide range of things that happened to be memorized by the model that you can imagine that if the model was trained on something other than the public internet, let's say individual people's emails or text messages, you would expect a similar amount of memorization, but just the memorization would be of a different type. It would be, instead of only data from the public internet, it would be memorization of people's emails. And because of the amount of how different the type of memorization was, we would expect that if it was trained on someone's emails, it would memorize very different kinds of content from people's emails. And this is, I guess, one of the interesting takeaways. The other interesting takeaway that I want to spend the remaining time talking about for this paper is how the memorization actually happens as a function of training data repetitions, which is the question, I guess, that we were just asked a minute ago. So let me walk you through this one experiment from the paper in a little bit of detail. So what we do is we find a single document that was on the internet that was included in the GPT-2 training data set. This one document had a bunch of URLs repeated between 8 and 359 different times. So what we can do is we can ask for these URLs that were in this training data set, which of these can we extract with the model? So we sort of run our attack a bunch of times and we check which of these URLs are in the training or in the output of the model. And it turns out that the model is more than happy to omit all of the sequences that appear 33 times or more. And so from one perspective, for this kind of content, for this kind of URL content, here's a threshold. If you insert something 33 times, then it's memorized, and if you don't, then it's not. Okay, so this is kind of nice to know, but we can actually do one better, in that OpenAI trained not only one model. This is what they call the XL model, the 1.5 billion parameter model. They also trained a 300 million parameter medium-sized model. So we can do the exact same analysis on this medium model. And here, we get much less memorization. This model memorizes only things inserted 56 times or more, and even then only some of the times. It doesn't memorize two of these things that are inserted 76 to 72 times. So this is interesting, smaller model, less memorization. And we can do one more time. They also trained a 100 million parameter model, their small model. And this model only barely memorized the one sequence that was inserted 359 times. And this is especially interesting because this small model, even though I'm calling it small, is still 100 million parameters. This model is like 400 or 500 megabytes on disk. This is, like, in absolute terms, quite big. But still, going from 100 million parameters to 1.5 billion parameters, you get an order of magnitude increase in the amount of memorization. The smallest model memorizes things that are inserted 300 times. The biggest model memorizes things that are inserted 30 times. So we're going 300 to 30, but the scale is going up from 100 million to a billion. And the reason this is especially concerning is that if you sort of look at the trend of model sizes over time, what you see is, like, the model that we attacked is the one here in 1.5 billion parameters. And we've already have models today that are 1,000 times bigger than this model. And 1,000 is a very big number, especially when compared to the fact that the difference in size between the XL and small is only a factor of 10. And so if you were to imagine adding like 9 more columns to the left of this XL, this is essentially what we're trying to do in the models we have today. And so I would imagine it's very, very likely that the models we have today memorize things that are inserted many, many fewer times than the 33 times that were necessary for memorization in GPT-2. Okay, so this is it for the first half of the talk, and for this paper. I want to pause here and take any questions on this piece before I move on to the next piece.
Vinu has raised his hand. I'll just try to unmute him. Vinu, can you ask your question?
Yeah, can you guys hear me?
Yes.
Yeah, so I just this data makes me think about a paper by Vitali Feldman, which says, does learning require memorization, a short tail about a long tail? That paper says you don't need to memorize examples which come from a typical subpopulation, but you need to memorize examples from rare subpopulations. And here it looks like it's the opposite. Are these two contradictory, or I'm not able to grasp both the things at the same time?
Yeah, right. The Vitali's paper is very nice. I don't necessarily think that they're contradictory, in part because most of what is in the GPT-2 training data set is like natural English text. Like just sort of people writing news articles or text conversations between people. And a small subset of that is URLs. And actually the context of these URLs is not URLs in any normal setting, but this is a JSON file that happens to contain a bunch of URLs. So you can imagine that most content in the GPT training data set is not JSON. And so if the model wants to assign a low loss to this particular training document that has these URLs repeated many times, it's going to have to memorize the JSON because it's sort of so far out of distribution for normal text that that's the only possible answer it has to do. So I sort of see this as supporting each other in this way.
Okay. Yeah. So the JSON format itself is so rare that it's coming from a atypical subpopulation.
Yeah, if I were to try and rationalize it, that's what I would try and say. I would also say that here again, we're sort of biasing things because we've repeated these sequences many, many times also. So it's not just that these occur once in the data set, but they occur many times, which again encourages the model. Like if the model wants to have a low loss, you can either find 359 random sequences to decrease the loss on, or you can take this one sequence and drop its loss by the same amount, and you'll get 100x better reduction in loss by doing this.
Mm-hmm. Okay, got it. Thank you.
Yep.
Thank you, Renu. So we have just one more question,
Sure.
Nicholas, on our Q&A tool. So Mukit says, is it true that language models trained on repetitive text get better likelihood or text which is not repetitive?
This is a very good question. We have a paper on this. We have a paper with some other people called Deduplicating Language Models Makes Them Better, or something like this. Deduplicating language model training data sets makes language models better. I'm butchering the title, but the answer is that if you train on data sets that do not have duplicates, then the perplexity of the models on the test set is not harmed, sometimes improved by a tiny bit. But also now you can sort of somewhat remove some of these privacy problems. And you also make the models train faster because they train on less repetitive text. And so it's just sort of better all around.
Awesome. Thanks, Nicholas.
Yeah. Okay, great. Maybe let me continue for the last 10 minutes of the talk, and then we'll do questions one more time. Okay, so this leads to the actual question: what are we going to do about this? Right? Here's a problem. The problem we have is that we have memorization in language models, or in neural networks more generally. How are we going to solve this? And what I'm going to do is I'm going to tell you about one particular type of defense that people have been trying recently that doesn't work. And we're going to do a training data extraction attack on this kind of defense. Okay. So this defense is a paper that is from ICML last year. It's called Instahyde. And what it's going to try and do is it's going to try and basically give you a way to protect against these kinds of attacks in the case of image models. So you're going to pivot from language to image and try and consider things there. The reason that this paper is interesting is it received a bunch of attention. It won this Bell Labs Prize second place, and people generally considered it something that is worth trying to use to defend against these kinds of attacks. So I wrote a paper with again a bunch of other people, big collaboration, where we tried to analyze the privacy of this scheme. In the paper, we have both theoretical and empirical results. I'm not a theory person, so I'm not going to try and butcher their theory. Instead, I'm going to do the sort of talk through the attacks. So let me explain to you what the Instahyde algorithm is going to do. What it's going to have is it's going to have a private data set of images that are sensitive, that you care about, and then a public data set of other images from some other data sets. What it's going to do is it's going to take two random images from the private part and two random images from the public part. And then it's going to combine all of them together and smash them together to form a single noisy image. So we're going to do this operation where we take these images, merge them pixel-wise, and get a noisy image. And now I'm going to do this random bit flip thing. And for each color channel of each of the pixels in the image, I'm going to randomly invert it or not. An invert here means swap 0 to 255 to go the inverse way, 255 to 0. Now I get a very noisy image. This image looks nothing like the original, and the claim is that it doesn't actually have anything to do with the original private data, really. And so I'm just going to put this over to the side. Now I'm going to do this again. I'm going to take two new images from the training data set, two new images from the public data set, smash them together, get a noisy image. And I'm going to repeat this many, many, many times. And now what I have is a big giant data set of what looks like pure noise. And then they have some other label, equivalent label mixing thing that's going on to construct the labels for each of these images. I'm going to ignore that piece of it because it's not relevant for the privacy implications, just the utility. But it turns out that it's possible to train a machine learning model on these completely uninterpretable images that is still accurate. This is kind of surprising, right? These images don't mean anything to us, but it turns out machine learning models can still learn on these images to get relatively good accuracy results. And so the claim is that these images now are privacy preserving. And that what you can do if you wanted to train a machine learning model is to just give someone else these images directly and say, here are these images, please train me a model. And they can do that, and it will have nothing to do with the original training data set. You won't be able to recover the original images. So the claim here is a stronger claim than the model, than just the model. We're not claiming, well, the Instahyde algorithm is not claiming the learned model is going to be private. It's claiming these particular images are going to be private. And so what we're going to try and do is we're going to try and show that given these images, that we can use this to recover the original image. And this is what the attack is going to try and do. It's going to try and go from noisy input image to clean output image. And the reason why the image on the right is blurry is because I've sort of blown up a CIFAR10 image to be really, really big. And so this is actually the highest quality image you'll be able to get out on the right. It turns out that if you run their attack on larger scale images, it's easier. And so the hardest thing to do is attack their classifier on smaller scale images. So we want to give them the benefit of the doubt here. Okay, So the way we're going to do this is we're actually going to do a two-step attack. The first step in the attack is what we're going to call clustering. And what clustering is going to do is it's going to try and predict if two encoded images, these are the noisy bit-flipped images, have an original image shared in common. Okay, so what I mean by this is, remember that the image on the left, this noisy image on the left, there are two private images that were used to derive this image. And on the right, there were two private images that were used to derive this noisy encoding over there. Now, we don't know what those encodings are normally, but you can imagine trying to construct a function that outputs 0 when there are no images shared in common here. But if you were to have the setting that the same image was used, the same private image was used on both sides, then this function would output 1. So this is a function that essentially lets us, say these two images are encoded. I don't know what the images are, but all I'm going to know is that they share an original image in common. Okay. How are we going to construct this function f? We're going to train it by ourselves we're going to create our own sensitive data sets with our own private images on our own public images, where we know the ground truth answers. And then we're going to just train a neural network to do this for us. So why should we believe it's possible to train a neural network to do this? Well, recall that it's possible to train on these encoded images to train a good classifier. So in some sense, these encodings are friendly for neural networks. For whatever reason, we don't necessarily need to know why. It's possible to train neural networks on these encodings. So we're going to train a neural network on these encodings, but instead of asking it to learn to be a classifier, we're going to ask it to learn to be something which can cluster together images that are similar. So we train it with some, contrastive loss that identifies similar images and can accurately do this task with something like 98% accuracy. And what this means is that now if you give me a bunch of encoded images, I can sort of pairwise between all of these images, ask which of these images are sort of share an original image in common. And then I can cluster them together. And I can say these 4 images on the left all have one original image in common. And these 4 images on the right all have one of these private images in common. And I still don't know anything about what's actually contained in these images. But what I do know is that they have something in common. And the reason that this is very helpful is that now I know that there exists an image which contributed to all of these. And it was constructed by doing some kind of regular adding, each of these encoded images was just a bunch of images added together. And so essentially all I need to do, it's a little more complicated than this, is I just need to smash them all on top of each other and just compute the pixel-wise average. And this will basically recover the original image. Because remember, what we have here is we have component of private image 1 followed by some other stuff. And then the next encoding is component of private image 1 followed by some other stuff. And then the other one is component of private image 1 followed by some other stuff. So really what we have when we consider all of these in aggregate is a lot of contribution of private image 1 and then a lot of other noise. And by averaging these images together, what we end up doing is we sort of average out the noise and we're left only with the signal, which is the image that we cared about. Now in practice, we need to do a little bit more details here. Because there was this sign flipping thing, we need to take the absolute value in order to make sure we can prevent that from happening. And then we do some other extra gradient descent steps just in order to get higher quality results. But this is essentially what we need to do and actually to make the attack work. And it works quite well. Here we have is on the top row, some original images from the training data set. And on the bottom row, we have the images that we're able to extract. And they're not perfectly accurate. If you look at the tower, you can see the color on the top of the tower is a little bit off. The original is a little greener and the extracted one is a little grayer. But for the most part, these are really, really high quality extractions. And these extractions are actually from a challenge data set that the authors released. And so this is not like our own set of results here. They released a challenge saying, can you solve this? And we said, yes, here's the answers. And because it's a challenge, they actually didn't release the original images. But it turns out that they did something cryptographically insecure. And so we could actually perfectly reconstruct the original ones with like a separate second attack. Now, I haven't told you about it all, but like it's a cheating attack just because of some implementation details that allowed us to get the originals. The extracted one is actually using the attack that I just told you about just now. And we can do this for lots of images. All of the images look fairly good. And sort of the basic lesson here is that ad hoc privacy is very hard. And you can construct things that look entirely reasonable, but don't actually give privacy. And it's not just Instahyde which is doing this. There was this more recent proposal, something called NeuroCrypt, where people tried to do a very similar kind of setup. And we attacked that. And we're able to do a very similar kind of reconstruction attacks here. This one, the privacy game is different. It wasn't a reconstruction privacy game. It was a re-identification. If you're interested in these kinds of attacks, I'd encourage you to go take a look at the paper. But yeah. Okay, so this is really sort of concerning because we ideally would like some kind of defense. So what's really left? And the answer, like 2 years ago, I said by using differential privacy, we could solve everything. And in principle, this is true. Today, it's not quite true yet. Not because differential privacy doesn't work. It does. Like it's sort of a correct defense. But the problem is that there are some fairly technical issues of how you define records. I don't want to get into this too much, but if you have duplicate training data, things get hard with differential privacy. And also, currently at least, differential privacy slows you down by a lot and makes you lose a bunch of accuracy. And the only reason we're using big models in the first place is because bigger models are more accurate. And if you're telling me here's a thing that will make you slower, I'll have to use smaller models because that's what I need to do in order to be able to train the same size model. And I'm going to lose accuracy. It's going to be a very hard sell for machine learning researchers to tell them here's this thing you can do. It only makes everything worse. It also helps with privacy too, which is a nice thing. But this is not something that a cost-benefit analysis people in machine learning space are likely to want to take. But at the very least, it will solve the problem. It just is going to be difficult in some of these ways. And I hope that people can fix this so that we can actually use differential privacy as a very, very nice defense. Today, at least, we don't have any other privacy training techniques that work other than differential privacy, basically. Okay, so briefly conclusion then. I think basically the next step, we need to better understand how memorization happens in neural networks, because we don't really. We have some intuition about what's going on, but I don't actually feel like we know why neural networks memorize training data. The paper mentioned by Vitaly is some very, very nice work in this direction, and I hope more people can try and figure out what's going on with memorization. And then after we understand that, we're going to need to be able to construct defenses that work. In particular, I think some forms of differential privacy that will scale more accurately is one leading way to do it, but I'm not going to rule out that as the only way. There might be other possible defenses that might help us here. But we're going to need to do something because the machine learning community is going to continue training bigger and bigger models. And this is only going to make things worse for privacy. And so we're going to need to find some way to address this problem. So thank you, and I'm happy to take any questions with the remaining few minutes.
Thank you, Nicholas, for the awesome talk. So I request the audience to please put in your questions or raise hands if you want to ask any clarification questions or some future direction questions. Maybe as we wait for the audiences to post some questions, maybe I can start. So Nicholas, you mentioned about these different models, like GPT models for different sizes. So one thing that we may draw parallels with is the overfitting and the underfitting notion. And do you also see a trend, or did you see a trend in these memorization techniques and your analysis in your previous part of the talk, where you found out that overfitted models act in a certain way as compared to underfitted models?
Yeah, this is a very good question. We haven't addressed this that much because all of the GPT-2 models are like not overfit in the traditional sense. So like when people traditionally say overfit, what they mean is like validation loss is substantially higher than training loss. But the GPT-2 models are not overfit in this way. Like their validation loss is still decreasing when they stop training. And we didn't perform any experiments that directly looked at what happens if you intentionally overfit models, because we don't have access to an overfit GPT-2.
I see. Thank you.
But yeah, no, this is a very interesting question. In some prior work, we looked at the relationship between overfitting and memorization. And basically what we found is that overfitting is not necessary for memorization. If you overfit extensively, then it's likely you're going to be memorizing, just sort of definitionally. But it's possible to have models that are not overfit, and I guess that's what we see here in this GPT-2 case, that these models are not overfit, but also still leak some private training data.
Right. Yeah, and that makes sense. Okay, so we have Matt who has raised his hand. So yeah, Matt, feel free to ask a question.
Hi, can y'all hear me?
Yes.
So you notice this observation between model capacity and sort of membership and inference for language models. Does that also hold for vision models? Bigger models are easier to perform membership inference?
This is a great question. There is no result on this that's okay. If you wait like 2 weeks, we will have a paper that's not primarily addressing this question, but we'll have some experiments that show that yes, this does happen.
Okay.
But yeah, so like there are some membership inference attacks that exist in the literature for vision. They kind of work. We're going to introduce a membership inference attack that works a lot better in just a little bit. And yeah, we see some nice results about scale too.
Okay, cool. Thanks.
Yeah.
Thank you, Matt. Yeah, so we have a bunch of questions in the Q&A to Nicholas. Berniers asks, do you have any references or blog posts going further in detail on the issues and progress with differential privacy for ML?
Sorry, issues for what with differential privacy?
Issues and progress with differential privacy.
Yeah, so there's a very nice blog post by some of my co-authors at the Berkeley AI blog that talks a little bit about this problem of differential privacy. Where, yeah, again, differential privacy is good. This is what we want. But if you just look at the implementations currently, they cause things to slow down, and it's sort of this privacy utility trade-off that exists. And this is the thing that I think we're going to need to do some work on to improve.
We have a next question where Luke asks, do you think there are any domains where memorization would not be a security or privacy issue?
Any domains where memorization is not a security problem? Sure. Yeah. If the data set you have is like, let's imagine a setting where I have a machine learning model that is trained on a data set where the data set is released along with the machine learning model. I don't care if it memorizes all of the data set because I'm giving it the data set for the people to download. So yeah, this definitely could be possible. And then you shouldn't be worried at all. Because if someone really cared, they could just like grep the data set to find something bad. But I think that what we're starting to see is lots of cases where people would like to be able to release machine learning models when they wouldn't have released the original training data sets. And that's where we need to be a little bit concerned.
Yeah, thank you for your answer, Nicholas. Akshay Varun asks, thanks for the great talk. And could you describe a bit more the dataset that was used to train the classifier during the clustering task? How many examples were needed and how similar they are to the examples that were supposed to be hidden?
Yeah. So when we trained this clustering thing, we trained this model on CIFAR10 images. So like we constructed our own data set on using CIFAR10 images, CIFAR100 images, and STL10 images, I think. And then we attacked at the end, like when we're doing this attack is actually on a data set. We don't know what the data set is that it was used to attack. The authors of the paper released a challenge where they said, we have gathered some images from some data source. We're not going to tell you where, that we're using our private images, and please attack these images. And so we don't actually know where the challenge images come from, but we assume that any challenge image that exists out there in the world is probably something like CIFAR 10 or CIFAR 100 or STL10 or one of these other small image data sets. And so that's why we tried to do this on a similar data set to source, but we don't actually know exactly what we end up with.
Thank you, Nicholas. And we have one more question from Varun. Varun says, did you have any experiments or conclusions on how model compression or distillation is affected by your attacks?
Yeah, this is also a very nice question. In this paper, we didn't look at this at all. In some prior work, we found that at least very simple forms of compression and quantization don't remove memorization. But we only did this as like one paragraph in a paper. There's probably more to be done than just a paragraph of research on this topic.
All right, thanks. So I think we can take one more question, and then we can go to your research journey.
Sure.
So yeah, Xiao asks, since the attacks needs two models trained from the same training set, would it be considered safe if only one model is ever released?
Yeah, okay. So this is going sort of back to the beginning here. We don't actually need two models trained from the same data set. What we need is two models. It doesn't matter necessarily where the other one comes from. So you can imagine that F1 here is GPT-2, and you can imagine F2 is BERT trained on something else. Or you can imagine that F2 is like, we did like zlib text compression. Or you can imagine F2 is like, ask a human, is this text good or bad? We need some other likelihood score in order to be able to say which things are abnormally unlikely. It just so happens that because we had GPT-2 and we had multiple variants of it, it worked very nicely to look at. This is what this table here is actually showing. If you compare across the rows, each row here is a different other F2. And so what you see is that doing various other things as the other model F2 can give you different levels of accuracy of extraction. And some of them are a lot better than others. So like just using straight perplexity is very, very bad. But comparing against GPT-2 small or zlib or these other fancy things we call window and lowercase are much better.
Perfect. Thanks, Nicholas. So I think we still have a bunch of questions coming in, but I'll take this opportunity to maybe ask you some your ML research journey questions so that it will be helpful for our young audience to learn from your research journey. So we have one signature questions, and it goes by, can you talk about your research journey a little bit and what motivated you to do what you do today, that is researching in adversarial attacks and privacy, and what motivated you to become a research scientist?
Yeah, okay, let's see. So I started my PhD doing research in system security, where I guess I always liked attacks. I've liked doing attack work forever. And when I started my PhD in system security, what I was doing is I would find people who published defenses that said, here's a way to prevent exploits from running on your hardware. And then I would go and I would say, it turns out that here's this interesting property of the CPU you didn't really realize. You can actually exploit it in this other way. Or people would say, here's a way to prevent Turing complete computation in attacks. And I'd say, well, it turns out, printf is a Turing complete subroutine in C. This was fun. I like doing this, but I wasn't exactly sure where this was going for a dissertation. And so I decided to switch to an area where, people have been working on software security, these kinds of things for a long time, 30 years. I decided to switch to an area where there was a lot less work, and that was machine learning at the time, and decided to see what kinds of attacks could be possible there. And I kind of ended up in machine learning, sort of going through I did a first attack on speech recognition that like I wasn't even thinking of this as machine learning. My advisor actually had a grant for wearable computing, but like we were thinking, you know, this is at the time of like Google Glass and these kinds of things. We were thinking if you have something that like you're wearing that you can't touch, you probably have to interact with it through speech. And so we're trying to come up with attacks that would allow you to attack this by like tell your device, like I could tell your device to pay me money without you realizing it. And of course, if you're doing this, what you're essentially doing is you're doing an attack on a machine learning classifier. We just didn't really think of it that way at the time. But then we went sort of full into the machine learning space. And yeah, I just sort of saw it as another area where I could do attacks, but it didn't seem like there was a lot of good work going on. It was still very early. And I liked breaking things, and I had seen some defenses that just seemed sketchy. And so I decided I'd try and attack those. And it ended up being a much bigger deal than I thought it would be. And yeah, things sort of just went from there. It was, I don't know, some people I feel like have sort of grand visions for what they're going to do. Like, I don't know, a while ago I was listening to a YouTube thing of a Google Tech Talk by Jeff Hinton in like 2007, where he's talking about unsupervised representation learning with like attending to the right parts of the image. And like all of these things, of course, now he's done, but this was like 15 years ago when neural networks didn't even work. And he was trying to get it to work then. I don't have this vision. I guess I just like analyzing whatever's in front of me. And it happened to be machine learning, and it happened to pick up a bunch. And I guess why Google, or like why research scientist? I like writing code. I like breaking things. I feel like that's a good. So I can still do these things as a research scientist.
That was very well put, Nicholas. Thanks. So I think the general takeaway is taking smaller steps towards the grand vision. Oh, perfect. So I think, yeah, one last question. So what is your advice for young PhD students who are just starting? And as you may know, in the current ML research, people are usually overwhelmed by the amount of work that has been done and the number of archive papers we are coming up every day. So what would be your advice to the young PhD students?
Yeah, this is hard. I feel like, well, first of all, I don't think I have any special reason to believe I can give any better advice than anyone else. Maybe ask someone who's a professor whose job is to teach people how to do a good job as young PhD students. But if I had to, if someone forced me to give an answer, I would probably say it's easier to do work at the intersection of two fields. I feel like, if you want to do really, really great work, let's say you have to be in like just machine learning. Let's say you probably have to be like, top 1% machine learning person to do like really great work. But if you want to do really great work at the intersection of, let's say, machine learning and security, like there are many fewer people who know how to do both. You probably, I don't think that I could say like, I'm top 1% in that field, but I probably am top 50% in security researchers and top 50% in machine learning researchers. And the intersection of these two people sets is small enough that like there are now very few people who do what I do, or now there are more, but like at the time there were very few. And so like that's, I guess, what I sort of lucked myself into. I would say trying to find this is a good way of being able to sort of feel less overwhelmed, because you can find areas where, machine learning touches almost every area. And you can really find problems where there are just not many people trying to solve them. And so if you actually understand both problems really well, then you'll be able to do good work. Because I feel like there's this trend, you have to actually understand both problems very well. Like there are a lot of really bad papers that get written by just machine learning researchers saying, I'm going to solve your problems in biology, or I'm going to solve your problems in security. And they write a paper that looks fine from the machine learning perspective, but just completely ignores all of the complication from the other field. You actually have to understand the other field. And I think it was a little easier for me because I came from the other field into machine learning. And actually, when I did this, I just didn't write any papers for 6 months. and just read machine learning research for like 6 months to be able to figure out what's going on in this new field, so that I felt qualified to do work in it. I feel like this is one way of just reducing like there might be tens of thousands of new papers to read on machine learning, but there are probably only a couple hundred papers to read on any particular sub area, and this might be a helpful thing. But who knows? Like there are lots of people who do great work and just go into just saying, I'm going to do great work in machine learning, and they do it. So I don't want to discourage anyone from just actually going, and if that's what you really like, then go and do it. But I feel like this is what worked for me. So maybe that's what I'd recommend, but I don't know, maybe survivorship bias or something. Yeah.
I think that is a great point, Nicholas, because I think one of the things that we as a Trustworthy ML Initiative, we promote is the intersection research between, let's say, different aspects of trustworthiness. So yeah, thanks for the great advice. And we are right on time. That is a rare thing we have. All congratulations to you.